Thank you for coming. So when Tyler and I were thinking about what to talk about, I didn't know what to talk about. He said he didn't either. So I said, well, let's split it up and do both. And I can talk about probably about 10 different topics because I'm a person who gets really bored with doing one thing. So I get involved with a lot of things. But I do work for Molex, the same company that Tyler works for. I'm part of our solid state lighting group, or I have been, although I'm working on a lot of really cool new things right now as well. But I've had a passion in super energy efficient building for about 35 years. When I was in college at MIT, I was studying initially nuclear engineering, but then I realized energy can be conserved and made in much better ways in the long run, so I became a mechanical engineer and was interested in how do you build homes that effectively use no energy. And in fact, I'm working with an architect that has been working for me for about 11 years now to design an off-the-grid house for the Morton Arboretum. So we've actually proposed it. They're very interested, but they also admit that they move at the speed of trees. So, so we'll see when that actually happens, but you know, I've learned enough things over the years that you can actually build a house that is extremely comfortable to live in. You can live as though you were living in the modern world with all the conveniences and still do it cost effectively and in a better environment than most of us live. The house that I built for myself and my family is in this article. I wrote this article for Home Power magazine 4 years ago. So it was published in, it tells you I think on the bottom, Home Power 151, so that's the article number. You could actually look up probably in the library. And so they basically came to me because I've met one of the fellows who works for their sister articles in magazines and said, can you write an article about your house? This is pretty incredible. And it really comes down to, it's not rocket science to build a home that can be literally net zero or literally off the grid if you want it to be. And over the last, I would say 5 years, it has been, I guess if you were living in a place where you didn't actually have attachment to a grid, you could actually say that it's extremely cost effective to do it there. I would say if I were building a house for somebody in this area, I would still attach it to the grid, but you could build it such that effectively it would be net zero. So a lot of the principles were developed in the United States in the 1970s, which is when I got interested in all of this, in the late 70s and early 80s. And then most of us that are probably at least 50 years old remember that the price of oil collapsed in the early 80s, and everybody forgot about the fact that you could build, you know, very smartly. But the technologies, even though they're not high tech, the methods of building today are much better than what was available 30, 35 years ago. So you can very cost effectively build a home that, you know, for instance, my wife, when we ever go anywhere, whether it's a hotel or stay with somebody else, she doesn't like it because of the fact that you've got air conditioners and heating systems that turn on and blast air. It becomes dusty. The air is dry in the winters. In our home, and by the way, we've had 3,500 visitors in the house over the last 10 years. And if any of you ever want to visit, just contact me. I'll give you a card and tell me you want to come out on a weekend, and I'd be glad to give you a tour. But I've done seminars for architects, builders, and they're amazed when they walk out because it's not rocket science. It's just common sense design. And there's a lot more detail in this article than we're going to be able to go over today. But I'm going to sort of go over the 5 critical things that you need to build a house that is extremely energy efficient. So, and by the way, I'll go back. My wife, the reason my wife absolutely says she could never live in another house other than like this is because you have constant flowing fresh air. It's quiet because you have very thick insulated walls. You've got sun coming in all the time, so it's very well day lit. And the quality of life, that's the hard part to describe to people. People talk about how much energy do you save. Well, that's very secondary to the quality of life. And that makes a huge difference. So if she has asthma and allergies, they basically aren't a problem in this house. So there's 5 things that you need to build an energy efficient house. I'm going to start asking you questions. Who can tell me what one of them is?
Money and knowledge.
Money and knowledge? Well, knowledge is always important. You can't do anything without knowledge. And money, you need money for any kind of house, but one of the things people ask me is, how much do you need? How much more does it cost to build, yes, one of those, to build a house like this? And that's always a good question. I always tell people somewhere around 12% more than a typical custom-built home. That doesn't sound like a lot, because most people have heard, oh, you know, it's 3 times as expensive. And if you listen to the people who are LEED certified, the LEEDs people, and I'm not a big believer in LEEDs, I'll tell you that right now, and I know some of you may come to other meetings and listen to people talk about LEEDs. LEEDs, when I read about what LEEDs talks about, what they do is they say, you're going to get so many points for hanging a bicycle rack on the outside of the door, so many points building near a train station. But really what's important is the longevity of the building. How well is it built, so you don't have to replace windows, so good quality materials, and how little energy does it use. They don't put enough emphasis on that. And that is really the long-term cost of a house. Eventually, you know, right now energy is cheap, but eventually it won't be cheap. So LEEDs, when I read all the articles about LEEDs, do one of you want to come up here? Because you're right behind a pole. I won't do anything that'll embarrass you, I don't think. So anyways, LEEDs talks about how much money does it cost to get a point in their system. And the numbers that I'm hearing is it's anywhere from 15 to 20% more to build a house that meets a LEED certification. And if I can tell you that give me 12% more, and I'll design and build you a house. I'm not a builder, but I help design houses with an architect. For 12% more, you can get a house that is not only extremely comfortable to live in, but it also will use 80% less energy for heating and cooling. So, and you don't have to have a LEED certification to do that. It will meet what's called the German Passive House Standard. So my objective, and the Germans have it right, they really figure out how to minimize the energy use, and they also will admit that they weren't really the first ones to think of this. Really, in the United States in the 70s is what really got Dr. Feist thinking about the German Passive House Standard. And they've taken it further, and I think I've taken it and figured out a way to reduce the cost of implementing it in the United States. So the first thing that you have to do in a very energy efficient house is insulate it extremely well. Insulation is actually by far the cheapest way to reduce the cost of energy, and also the cheapest way to actually build a house that is very comfortable to live in. So most of us live in a house that has a wall that thick. It's about 3.5 inches thick. And they put a little bit of fiberglass insulation in there, and they say, this is your house. And to keep that kind of house comfortable, you have to have a really big heating system, a really big air conditioning system, and you can make up for having a house with a wall that thick, the inefficiencies in it, by having cheap energy. So basically, we're used to having energy that is cheap. And it's even cheaper now than it was a couple years ago, but it won't always be cheap. And the problem is, when we build a house today, most of us think, oh, we'll live here for 7 years and we'll be out of here, so why would I spend more money on building a nicer house? But the truth is, that house is going to be standing, hopefully, 75, 100 years from now, and somebody is going to be paying through the nose for energy and the bad windows that had to be replaced, and the roofs that had to be replaced, and it's going to be really difficult for society to justify those kinds of homes. So a lot of building homes well is using extremely good quality materials. But having said that, you want to use materials that are commercially available. So in some cases, the German passive house standard comes up with these exotic ways of making walls. And even around here, you know, people will say, I want to make triple walls, double walls, do this, do that. They're techniques that aren't commercially available. So my philosophy was, and if you take a look at this article, by the way, that's the picture of the house, and that faces south. 12% of the south-facing, 12% of the floor area of the house is south-facing glass. So anywhere from 10 to 15% is the right number, and we're actually going to get to that in another topic. But if you take a look at page 4, under cost of insulating, what I did is I went and I looked at all the different methods that are commercially available for insulating in the United States. Extruded polystyrene, polystyrene SIPs, urethane SIPs, I-joists, double walls, ICFs. There may be some others. And I looked at the cost per square foot and the R value. Why don't you take an article here? And what the cost of installing that wall, that square foot of wall area is approximately. And then I divided the R value by the cost, and I said this is the cost per R value. Somebody, I don't know if anybody's ever done that before, but does it make sense why I do that? And the reason is insulating value of your walls are what determines how much energy you're going to lose through that wall when it's cold. And if you can get as much as you can afford, least expensively, that's what you want to do. Because that's where energy goes, that's where the comfort level in your house is. So you want to minimize losses through the wall at the lowest cost you can do it. And you want to have the right kinds of insulation. So I insulated under the floors, along the walls under the earth, along the walls against the air, and then on the ceiling. And every location, I added more and more insulation as the temperature difference across those got greater. Is this getting too technical?
No.
No? Are you okay? Tell me, because I can go minimal or I can go deep. So insulation, that's number one. Rule number one, do the most you can. And if somebody wants to spend time with me on that, I'd be glad to talk to you about that more. So number two is orienting the house in the right direction. My undergraduate thesis was optimizing energy flux through windows. My master's thesis was on indoor air quality and super energy efficient homes. So I really got into this, and I use those are windows facing south are a phenomenally good way of getting energy. It's, you know, you get about 1,000 watts of energy per square meter on a sunny day hitting a vertical window. 1,000 watts. That's a lot. So what you want is a window that allows that energy to come through. So you have what's called high solar heat gain glass facing south. And you want it to be 50 to 60%. Most windows, if you go to a Home Depot or Menards or whatever right now and go buy a window, they put soft coat, low-E coatings on it. And that blocks the sun. Because most people build these houses all over the place here, these McMansions we build, and they face the windows west and east and north and, you know, whatever direction. If you face a window west, guess what? Your air conditioner bill went straight through the roof because you can't stop that sun from coming in. There's no way to put an overhang in, and all those windows are gaining a massive amount of energy, and you got to get rid of it with air conditioners. So the key is you put minimal windows west, minimal windows east, minimal windows north, and if you do put them there, you use triple pane glass with soft coat low-E. If you're going to build a passive solar house, which is where you get a lot of energy if you're going to build a house that's really efficient, you build 10 to 15% of your floor area of your house to south-facing windows. And you use high solar heat gain glass. And now you can buy triple pane windows that are high solar heat gain, 50%, 60% of the energy coming through. So that's rule number two. So you've got a very insulated thermal envelope, and you've got south-facing windows, which is exactly what you see, you know, on the front of the house here. Then rule number three is you use the temperature of the earth. So all of us have two free sources of energy. One is the sun, which we just talked about. The second is the temperature of the earth. So if we dug down here 8 feet, what's the temperature roughly?
55, 60.
Right. In the summers it may be 55, in the winters it may be 45, but the average is 50 degrees. Why is it 50 degrees? It's because it's the average air temperature of our area. So in the summers, the average temperature may be 75. In the winters, it may be 25. Guess what? The yearly average is 50. It doesn't change that much that deep down because you've got so much thermal mass. So think of the Earth as a huge thermal capacitor. It collects the energy from the sun and stores it in the Earth. And all of us have access to it. So years and years ago, I had a professor that I worked for, and he was a big believer in earth-sheltered homes. I was at the time because he was, but years later I realized, how many of you keep your house at 50 degrees? So the problem is, if you keep your house at 65 to 70, which I like 68 or so, but 70 may be normal for a lot of people, you're constantly if you build an earth-sheltered home and the earth doesn't have any insulation between you and the walls, there's two huge problems. One is the temperature difference, 20-degree temperature difference, and you have almost no insulating value in a concrete wall. It's like R1 if it's 4 inches thick. You're losing 20 BTUs per square foot per hour, which that's just the way thermal resistance is calculated. If your R value is 1 and your temperature difference is 20, you're 20 BTUs per square foot per hour, all heating season. And guess what? You have a lot of surface area, you have floors. My house, this house here, is 4,500 square feet of heated space. And the reason we did it that way is we build it for people who are interested in this sort of thing to be able to come, see, experience. And at one time I thought I wanted to build houses like this. Now I realize there's no market for it, except for people like yourselves. And what happened is I built it sort of as an environmental bed and breakfast for people to come to see. But it's 4,500 square feet, much larger than we realized we were doing and needed. But that's also including the basement, which is a walkout. So around here, it would really be considered a 3,200 square foot house. But it would normally have a 200 to 250,000 BTU heating system. Instead, I have 15,000 BTUs. So one winter, we turned off the heating system completely and left, except on the weekends we'd come back before my wife was living there full time. And on an average sunny day, it's between 68 and 72 degrees all winter without a heating system. And the coldest it got all winter was 55 degrees. And the reason is you got the temperature of the earth. And it's, if you take a look at page 6, that was when we were building the house, and that is what I call the earth room. So if you take a look at the end of that picture, you see a little black pipe coming out. That's where the fresh air comes into the house. It goes down and into that little hole that you see in the wall, and it flows 50 feet along that length, and that room is 50 degrees. It's my thermal capacitor. So all my fresh air, I have a system that's constantly bringing in fresh air and exchanging it with the air from the bathrooms and in the kitchen. So I don't have an exhaust fan anywhere or anything. It's just constantly moving. You can't hear it. You can put your hand up to the little opening and you'll feel the air coming out. But it's always moving at about 300 CFM. And if the heating system or the air conditioner needs to come on, and that's not very often, it will actually increase to about 800 CFM. The difference is now it could be 10 below zero outside here. By the time it goes through this room and into my heat recovery ventilator, that air is 45 to 50 degrees because of the earth. I've collected that energy from the earth in the winter, and then I run it through a heat recovery ventilator, which is a heat exchanger, and that exchanges the air, heat from the air that was in the bathrooms and the kitchen, and that air now is 55 degrees, and I only have to heat it up to about 70. So I only have to heat it up 15 degrees, even though it's 10 below zero outside. So it's sort of magical. We've collected this energy from the earth in a way that's completely passive, without all sorts of geothermal heat pumps and motors and things that are going to break. It's all done very passively. Now in the summer, guess what? If it's 90 out, that air comes in at 55 degrees, cooling the house. So there's a lot of advantages of having an earth room in the summer and in the winter. In the fall and the spring, it's not as much because the temperature gradients aren't as big. So constant moving fresh air, temperature of the earth is very, very important. The other thing is sealing the house. Having windows that are extremely well sealed, doors, like for instance, if you walk into the main entry of the house, I think if you take a look at the picture, it's not really shown there. But anyways, just like in years ago when they built farmhouses, you had mudrooms. Well, mudrooms are basically a place to take your boots off and hang your coat, but they also isolate the temperature in the summer from the rest of the house, and in the winter from the rest of the house. And that the walls of that mudroom are insulated, just like most of our houses are today, you know, with a 2x4 wall. So I'm effectively creating another barrier from the actual heat or the cold coming into the house. So those are really the main things. The fifth item is, after you've done all this stuff, you know, again, in the first sentence I think I say it's 10 times cheaper to save energy than it is to make energy, no matter how you make that energy. So after you've done all these things to reduce the amount of energy that you need, then you go in and do what everybody thinks a solar house should be, is you add the solar panels. So today, the cost of photovoltaic panels has dropped to about 80 cents to $1 a peak watt. 10 years ago, it was $4.50 to $5 a peak watt, and it was really pretty expensive to do. Now, most of us, if we wanted to, and if we had a good south-facing roof, you could put solar panels up, and if you just grid tie it and do what's called net zero, not net zero, net metering, you could actually probably pay for it in somewhere between 5 and 10 years, depending on what rebates you get and all that. So it's really gotten to the point where if you have an installer who's not going to rip you off and do it correctly, it is really cost effective. You should be able to put panels up for somewhere between $2 and $2.50, fully installed a peak watt. So if you put, you know, 6 kilowatts up, which is probably a good size for a normal house, you're talking maybe $10,000 to $12,000 to do it. So it's really come way down. So, you know, it's so, I mean, I can talk about this for a long, long time, but if any of you would actually like to see it and experience it, and, you know, I typically do an hour, hour and a half type walkthrough through the house. You know, my phone number is either there or email, or there's a card there, you can always reach me, or reach me through Tyler or however. So, are there any questions on that? I mean, again, I can keep talking, but I think I only want to answer the questions you're interested in.
What brand are your windows?
Pardon me?
What brand are
I use, in this house, I use Lowen, Loewen. They're made in Canada. They're made out of Douglas fir, and they weigh twice as much as Andersons and Pelvis. So they're really good quality windows. But what I have found recently is that the price of the Lowen windows has really gone up quite a bit. And believe it or not, the windows that we're using for some of the houses now, and I have an architect that works with me, his name is Kevin Donovan, and we design 2 or 3 buildings a year. We have one in Minnesota that's being built right now, another one on a lake in Wisconsin. But they're big homes, 9,000 square feet, 5,000 square feet, and our belief is in the future is really 800 to 1,500 square feet. And that's what we're doing at the Morton Arboretum. We've got designs for those, but the people that have the money and are passionate and want to build a custom-built home, that's what they want right now. But these are two-year projects, and, you know, Kevin is employed doing it, but it's not what I believe or even he believes is really the long-term future of homes. What's sad about this area is go try to find a lot, first of all, that you can afford, because a lot probably down the street here, a quarter acre could cost you $120,000 just for a lot. And then on top of that, it has to be oriented correctly. And we've built streets in every direction you can think of. So to find a lot where you can get a nice, good southern exposure, you can afford it, and justify building an inexpensive, smaller home is hard to do. Now, if you go west, or if you get out of the metropolitan areas, then that makes a lot. And I'd love to be able to work with someone who wants to build either an off-the-grid or a net zero that is very small, very affordable. And I think that's really the future of both for younger people and older people. Older people who want to get out of their McMansions and live in a comfortable house, and younger people who just can't justify that, or there's a lot of good reasons to build smaller homes. So, a little bit about and I didn't bring any pictures about the off-the-grid house at the Morton Arboretum, but it's a little 2-bedroom, 2-bath. It's got an upstairs loft looking down into the living space. It's only about 1,200 square feet, and it has an attached greenhouse. So what we did is we attached a greenhouse on one end of it that uses a lot of the same methods that we're going to take a look at here in a minute. And I actually took the day off from work today because I'm working on an off-the-grid greenhouse for the Oregon-Illinois High School. We're actually going to move the building that we built 5 years ago for the Illinois Renewable Energy Association, and we're going to do it so that we actually earth couple it. The people who had it built then didn't want to earth couple it, and because they wanted to move it and show it in different places, and it just didn't turn out to be practical. So now the high school is actually going to go ahead and excavate a foundation. We're going to insulate the vertical walls, and we're going to keep the floor at earth temperature, 50 degrees. And now we're going to basically pull the air from that earth room. It's just like your basement. Your basement probably doesn't have insulated floors. And that floor is 50 degrees. So if you can keep your greenhouse at 50 degrees, guess what? You can grow spinach, lettuces, a lot of herbs, root plants. Now, you're not going to grow tomatoes, you're not going to grow peppers and some of the other warm plants, but there's a lot of things you can grow all year, and we have a couple of solar panels on the outside. They're going to use these LEDs that will power on 24 volts if you need to. And you can literally run these directly off solar panels. You do not need to have electrical outlets to the wall, even. So you can literally, what we're going to have is the windows that are facing south. And again, we did exactly the same thing in the greenhouse as we did in this house. We insulate the north wall, the east wall, the west wall, the roof. And then the bottom is sitting on, it's like your basement. We're pulling the air through there. We're actually going to grow mushrooms in that lower level. And then the upper level, we'll open the windows during the day. And then we have a photosensor that turns or closes, motorized, it drops the window blinds at night so you don't lose the heat through the windows. And we put, this is sort of something interesting as well. We put phase change materials into the wall, the vertical wall. So, does anybody know what a phase change material is?
No.
So if you take a stick of butter and you put it on a table, taking it out of the refrigerator, and it's 95 degrees in the room, what happens to that butter? So what happened was that butter went through a phase change. It went from a solid to a liquid, right? So when it does that, just like water, if you take a pot of water, and if you put a thermometer in that pot of water when you're boiling it, what's the temperature of the water? 100 degrees C, right? We're at 212 F. So it's going through the phase change. It's using a huge amount of energy to go through a phase change. So there's two phase changes that occur. They occur from solid to liquid, liquid to vapor, right? So both of them take a huge amount of energy, and the temperature stays exactly the same. It's stable. So if you could take phase change materials, and there's a house built in Grays Lake that I did some consulting for. Patsy Wells just finished the house. And what we did is instead of a trommel, which is what she wanted to do, and guess what? It's the phase change material melts at about 80 degrees. What it does is it melts during the day when the sun is hitting it, storing all that energy, keeping the house from getting too hot. At night, we have air flowing across those phase change materials and effectively taking the energy out of them, keeping your house warm at night. So it's a passive way of effectively keeping your house at a very stable temperature. Well, in the greenhouse, because we want it not to freeze in the winter, because remember, there's no electricity in this greenhouse, and there's no natural gas, nothing. It's just using some solar panels and the temperature of the earth to heat and be able to grow food passively. So by putting phase change materials in there that melt at about 45 degrees, when the sun comes in, it melts them during the day. And guess what? When the sun drops, and if it's 5 below zero out there, it's cold out there, but you've got the stored energy in this phase change material that's giving off its heat. Our whole objective is not to drop below 32 degrees for long periods of time, allowing the plants to freeze. We don't want them to freeze. That's the key. So the phase change material may not keep it at 45, but it should be doing enough between the temperature of the earth and the phase change to basically prevent it from basically freezing. So that's the objective, yes.
You know, this is a little bit different than the earth room, but I was sort of interested in the concept of geothermal, and is that something
Well, this is a type of geothermal system. So geothermal heat pumps in the United States, everybody thinks of a geothermal heat pump. And what it is it's basically, they take a working fluid, a Freon type material, and they dig a bunch of holes in the ground, and it can be horizontal heat pumps or vertical heat pumps. And then they have, a heat pump is really, an air conditioner is a heat pump, but only it works in one direction. A heat pump normally works in the summer as a air conditioner, and it works in the winter as a heating system. So it's just reversing the cycle. The problem with a heat pump is, that's a great question, because I think I'm going to try to explain this to you that makes sense. So all of us probably around here use natural gas to heat, right? That's probably the most common. You can go buy a natural gas furnace that's about 95% efficient, and it takes 95% of the energy that's stored in that natural gas and it heats the building. And that furnace costs you about maybe $5,000 to install. Now, you can go and buy a geothermal heat pump and have it installed for maybe about $25,000 in a house. So you've spent $20,000 more on that geothermal heat pump, hoping that you're going to get a payback on it, right? So here's the problem, is most of us don't do what's called a complete energy balance on this. So I can take that same natural gas that you burned to heat your house and burn it in a power plant. And that power plant creates electricity, which you need to run your geothermal heat pump. Now, the thermal efficiency of a power plant, whether you're burning natural gas, nuclear, coal, whatever, is by the time it gets to your house about 33%. The best is nuclear, which is about 40% at the power plant, but by the time it gets to your house, it may only be 34, 35, 36%. But just say natural gas is about 32, 33%. Well, what they're selling you on a geothermal heat pump is for every unit of energy you put into it, you get, on average, about 3 times out. That's their big selling point. Now, if you're burning electricity to heat your house, you already made a big mistake by using pure electricity. It's not a great way to do it. A heat pump is a good way to reduce that load. But what I'm saying is that 3 times benefit times 32% is about 95, 96% efficiency. So guess what? You've gotten the same total efficiency in your system as if you used that same natural gas and heated your house. So what I'm saying is natural gas is a really darn good way to heat your house if you have a good, efficient system. So you spent $20,000 more on that geothermal heat pump. If you took that $20,000 and put it in really good walls, really good windows, really good insulation, wherever you can, even if you had an existing house, put in really good windows and insulate wherever you can, you've reduced the amount of energy you need, and that will still benefit you 25 years from now. Whereas that geothermal heat pump in 15 years, you're replacing the pumps, the motors, and everything else. Does that sort of make sense?
Yeah, that's really interesting, thank you. That was,
Sure.
and actually, I also understood it, so thank you.
Yeah, don't spend money on a geothermal heat pump. So, you know, again, I could talk for days about this, or hours at least, but I think, is that a good enough? We can move on to the next topic here. So how many of you ever have tried growing anything indoors other than starting things in the spring? Have you had good luck in growing things indoors? And why do you think that's the case?
I don't have a lot of southern exposure, so the light is limited.
That's
And the house, like you say, it gets warm and it gets cool.
Right. So the three things you need to grow are light, water, what is that?
Something else.
Nutrients. So those are the three things you need. How you get them is really, you know, everybody has their own way of doing it. So, well, this is where I'm going to go through this, because this will give you a little more detail. So most of us have probably heard of conventional indoor or hydroponics. And I've always stayed away from hydroponics because you need pumps and motors, and you know, it always sounds like there's a toilet leaking somewhere in the house. And you know, I've bought systems that I've compared it to, and you still need light. It's sort of nice in that you don't need soil, but we'll talk a little bit about some of the other things that you could do. It does require pumps and motors and energy in some form or other. And it requires continual upkeep. So you've got to keep adding water and looking at the nutrients. Yeah, do you want to reduce
Do
that?
you know which one it is, Barbara?
It's the bottom one.
Just on the
Just
left?
pressed
or-
it. It doesn't matter. You can just press it, yeah.
Yeah, can everybody sort of read it now? Better? Okay, so this is where I was. You know, due to the drawbacks, it's really not a practical way. So I stayed away from it, even though I enjoyed growing things indoors. So potting mix, most of us probably have gone off and bought a bag of potting mix. And the problem I've run into with potting mix is, first of all, it's messy indoors. But the other thing is that a lot of the potting mixes aren't sterile anymore. And you start getting gnats. And we had bugs in the house, and it was, my wife said, get rid of it. You know, we don't need any more of that. So you've got to find a better way to do it. So I ended up switching for a long time, for about probably 9 months to a year, a mixture of coconut coir and vermiculite. Vermiculite you can go buy locally, and coconut coir you can get on Amazon, and they send you these bricks, and they expand about 4 times, and you mix that 50-50 with the potting mix. I'm sorry, with coconut coir and vermiculite you could mix. And you can then use hydroponic fertilizers, and that works better, but you still have to water it pretty regularly. And so I found there were some issues with that. And then you also, if it always sat stagnant, you could start getting mold or algae growing in it. And I said, I don't like that either. So there's some issues associated with those methods that I just wasn't real thrilled with. So I kept trying to find better ways to do it. So about a year and a half ago, I found out about a method, and I encourage you to get on YouTube and look at it yourself. It was developed by a professor from the University of Hawaii. His name is Dr. Bernard Krapke. I think his name is spelled up there. And he got his PhD from Purdue. He's a horticulturalist. And he came up with a way that I think is ingenious. And it's basically a passive hydroponics method that really simplifies the approach to growing indoors. And what he effectively did is he took various containers, And you can see on the YouTube, there's all these different things people are doing. I started with these 10-gallon tubs that I got from Home Depot. They're Rubbermaid, and I drilled 3-inch diameter holes, and I used 3-inch diameter net pots, but I've got 2-inch diameter all the way up to 6-inch diameter net pots that I use now, depending on what you're trying to grow. And a lot of people do it outside. Some people do it in big commercial tables, where they're growing all the same thing, and some people do it. So my father-in-law modified the process, and he said, let's do it in a canning jar. So it turns out that a 1-quart canning jar with a large diameter mouth, or they also have the 1-gallon ones, or half-gallon ones, that are all the same diameter. That's a 3-inch diameter net pot with clay pellets in it. Drops right in it. These are the little clay pellets. You can take the little lid out, screw the lid on, and you've got, depending on what you're growing, a quart usually isn't enough, but the half-gallons in some cases are enough. You can actually put all the water that the plant will ever need for its entire life cycle in there. If you're growing lettuce, certain herbs, here's a basil plant that basically probably is 5 to 6 weeks. Lettuce, in 3 to 4 weeks, I start cutting it, and I'm having salads. My wife and I, we literally took this baker's rack, and we have 3 rows of lights and anything we want to grow. I literally have cucumbers growing right now. I have beets that I've eaten. I've got broccoli that I've grown in my local apartment here. Carrots. Now, any root plants like beets and carrots you want to do in the coconut core and vermiculite, because obviously you want something that's loose and fluffy so that the root can actually form. But anything that grows up, these little clay pellets are by far the best way to do it. So the reason that this works is it's really pretty darn cool. It's completely silent, completely can be done off the grid. So this is what we're going to do in the off-the-grid greenhouse, because it doesn't require energy for pumps and motors. And the reason this works is that basically the roots go into the water, and in fact, unfortunately I brought the dark one, but the roots are way down here. So what happens is the roots go in there, they suck up the water, and the top of the root now is in here. So if the root was completely submerged, it would rot effectively. It wouldn't get its oxygen and CO2. But because it's in air, it's getting all of its air, which is a big part of what the plant needs to grow, from the roots and from the leaves. And if this weren't stationary, like a normal hydroponic system, they actually float it stays completely in water. But because this is fixed relative to the water height, and the top of the root is getting its CO2 and air, it works beautifully. And so, depending on what you're growing, and we're going to talk a little bit more about containers here. Now, we'll see that. So, here's the things that you need. You need whatever containers you need or want. You need some net pots. You need hydroponic clay pellets. I buy them actually in huge bags now. You need your fertilizer or nutrients. You need water. You need seeds, and you need grow light. So one of the reasons, you were commenting earlier, you don't have enough southern exposure. Well, even if you did have good southern exposure in the winter, guess what? The average day is only 6 hours long. So a lot of plants do not, even if you had a good southern exposure, would not work. So up until about 4 or 5 years ago, even the conventional lighting, my real job is designing solid state lighting, but horticultural lighting is even a little bit different. There's something called, have any of you heard of the word PAR, or photosynthetically active radiation? No? Okay, that's critical for plant growth. That's what determines if a plant's going to have enough energy or not have enough energy. So this is a pretty exotic, like $1,500 par meter. But I need it because that's what I'm showing people what to do. So this measures energy that is sensitive, that the plants need to grow, and it's between 400 and 700 nanometers. 400 is purple, 700 is deep red. And plants, unlike us, absorb energy at different wavelengths than we do. In fact, I think there's something coming up here that will describe that. This is just a list of other containers other than canning jars that I really like. This is a Ziploc that I think I got that at Walmart. It looks like that, and it's got a seal around the perimeter, and I use 2-inch net pots. And then Home Depot has these, a 3-gallon and a 10-gallon roughneck. This is the 10-gallon, and then I basically pop. I've gone as many as 9 holes in it. This one has 5, depending on what you're growing. This has 10 gallons of water in there. So depending on what you're growing, if it's a plant like a tomato or a pepper that takes a long time, or cucumbers, you may only want to put 1 bigger net pot in there. And I use 5-gallon buckets for a lot of that as well. But any kind of container that is opaque is ideal, because if it's not opaque, and this is one of the things I'll tell you about canning jars as well, is if you put them near the sun and it's warm, you can get algae in there, and that detracts from basically the roots. I am doing an experiment now that looks really promising. Believe it or not, grapefruit seed extract you can get in little containers. Put that few drops in there, and that appears to get rid of algae. It basically is a algicide. I'll have a lot more data on that soon. Now, the other thing I'll do is I'm going to pass around these little cards, and I have about 10 YouTube videos on my wife's business website that describes to you how to set a lot of this stuff up. And it just goes, and anytime I learn anything, I put that on there as well. So the necessary elements for growing a super easy indoor garden. You need water, and there you sort of have to think about what container you're going to put it in, what the pH is. You want a pH somewhere around 7 if you can get it to be neutral. If you're city water, you may have chlorine in there. You may need to leave it for a day or two sitting out in the sun. That's supposed to get rid of the chlorine, but you know, the truth is, I've used water from a lot of different places, and this seems to work in almost any kind of water. What I actually would recommend if somebody's not sure if their water is going to work is get a container of RO water, which you can get at a drugstore, or distilled water, and compare that to what you've got and see if there's any difference in how they grow. Instead of trying to analyze it and all that, I've done both. And then obviously you need your nutrients, so your NPK and the micronutrients. I do mix a lot of my own now with powders, but the easiest way, believe it or not, is to start at least, is I've tried about a dozen different fertilizers, and this is one you can get on Amazon, and it's made by a company called Kana, and it's called their Cocoa Part A and B. So a quart, two 1-liter containers will last, if you're growing for 2 people, you could probably get by for 6 months easily for that. So it's got a little measuring thing here, and you put in 15 milliliter, which is a teaspoon of each per gallon. So like that quart, you could fill 4 of them in almost a tiny, tiny bit. It doesn't take very much. And that has the micronutrients and the NPK requirements that you need in it. So, and then you need light. So this is probably the least understood. People have studied nutrients and water forever, but the problem with getting light, most of us are used to just using the sun. It's a great way to do it if you have access to it. But unfortunately, around here, you don't have it. And other people who grow things like pot and weed, they go out and they buy these metal halide or sodium vapor lamps, and they get caught because of the heat signatures of these really expensive lamps, and they'll spend hundreds of dollars a month on electricity bills. But LEDs in the last few years have completely changed the game. And if you've probably heard a little bit about some of these places, these vertical gardens, like in a place called The Plant in Chicago. There's another place in Valparaiso that grows a lot of the leafy greens. They're vertical indoor gardens. There's another one in Rochelle, near where our farm is, that they grow the tomatoes for a lot of the Chicago area now. And they're all doing it with LEDs, and they're all doing it hydroponically, typically active hydroponics. But LEDs are the magic that enable you to do it cost effectively. So I'm going to show you a few more things here. This is just a little bit more about water, well water, pH levels, city water, chlorine. Again, I would say just try it and compare it to using RO water or distilled water and see how it compares to whatever water you have and see if you see a difference. This is the same thing I just talked about with the two-part. And then there are some other fertilizers. This is, the biggest difference I have found is that this costs about 25 to 30 cents a gallon of fertilized water. If you mix your own, but you have to usually buy a little bit more. This is a company, it's called Master Blend, and they're actually located in Morris, Illinois. And they make a mixture, a powdered mixture that you need a teaspoon of per gallon. And then you can buy calcium nitrate on Amazon again, and Epsom salts, which is magnesium sulfate. And you mix this in the ratio that I show there, and it's less than 10 cents a gallon. So if you were doing a lot, this would be the cheapest way to do it. Oh, why is it not? So we talked a little bit about light and energy. This is the missing piece that for years wasn't available to the average person. The big growers would buy $1,000 lights. There are a lot of Chinese ones that you can get on Amazon that are absolute garbage, and I'll show you a couple of them here, or at least one of them. And so here's a light source that I actually designed at Molex, and it's a grow light. So, who's a volunteer? Anybody? Come on up. So this is sort of cool. And I'm going to show you two versions of a light. This one is this little magnetic puck. When you put it on, just don't look at it. And it's just because it's bright. And just slide it up in there. So there's, I'm not going to point it at you. Here, you can put another one on, that'll be easier. So basically, here, these are a mixture of red, thank you. It's a mixture of red and blue. And the reason is, our eyes are most sensitive to green light at 550 nanometers. But plants, chlorophyll A and B, are most sensitive to blue at 450 nanometers, which is, so this is our eyes sensitivity. This is a plant sensitivity, which is the PAR energy, photosynthetically active radiation. So 450 nanometers is here, which is blue. And you want actually about 75 to 80% of the energy to be in the red spectrum, because you want plants, that's what causes them to go vertical, and also to blossom. You cannot blossom without red energy. And blossoming is only necessary, though, for plants that produce a fruit. So tomatoes, cucumbers, peppers, anything that produces some sort of vegetative fruit. If you're growing lettuce, herbs, you could get by with less, but red actually works well too for chlorophylls. So typically you want between 15 and 18 hours. Typically you have a timer, you'll turn it on 15 to 18 hours, and it just turns it on and off every day. And you put it under the light, and I'm going to show you another light that actually has more energy per dollar. And this is the grow lights that I typically use now, although we use these too. And you can put up to 12 of these under there, or you can put obviously one bigger container. And as the plant grows, I typically like to, when the plants all are just starting, I'm 4 to 5 inches up. And as the plant grows, you just move it up and set it above it. You can put this in the basement, in the closet, in the kitchen if you want. I have all these different decorative containers that people could use in the kitchen as well, that I've tried and used. And I'm going to show you one other thing here. This par meter, here, you want to continue to help? Since you volunteered once, I'll keep you. So, actually, normally I bring a fluorescent bulb. What I'm going to do here, because it's like a T5 fluorescent that a lot of people use, and they're great for seed starting. And typically, to start a seed, you want between 30 and 100 micromoles per square meter per second. So those of you that had chemistry years ago, a mole is, what's the number for a mole?
What, 6.022 times
10 to the
10 to the
23rd.
23rd.
That's the number of photons, it's just a number, but that's the number of photons per square meter per second that this meter is reading, okay? So it's measuring what's called photon flux density in micromoles, okay? So I'm going to put a regular, what is this, 40-watt light bulb and show you the difference in the number of micromoles that you get when you try to do, okay, this is a kilowatt, so it's measuring wattage. Oh, okay, so how many watts are we reading here?
26.
26 watts, okay? And this is a par meter, so it's measuring photon flux density. So I'm going to hold this, and you're going to look at, I'm going to hold it about, let's just say is that about a foot? How many micromoles am I getting?
Here,
Yeah,
8.127.
8.27. So 40 watts, 8.27 micromoles. Remember I was saying you need between 30 and 100 to grow? Would this work? No. Okay, so now what I'm going to ask you to do is I'm going to plug the same kilowatt meter in here. And how many watts are we pulling?
29.
29. So is that more or less?
More.
That was 40, this is 29?
Less.
Less. Okay, so take that and put it about, put it under here about a foot down, same distance. Yeah, just hold that. And then tell me how many micromoles are we getting?
It's about 210.
210. So less power, 25 times as much energy. So that's why LEDs, great job. And you even know what a mole is.
Thank you.
My wife would have said it was a bug or an animal playing
I'm a
around.
science student.
Yeah.
I have an idea.
Okay, so you know. So basically, 200 micromoles allows you to effectively grow any kind of plant you want. And that's really the thing that LEDs have enabled us to do, which you couldn't have done before. Even fluorescence. If we did the same experiment, which if I didn't want to bring a big fluorescent system, I would have gotten 40 micromoles out of the fluorescent. Still better than that, but nowhere near what the LED does. So that's the magic that LEDs will allow us to grow food locally. By doing it this way, whether it's active hydroponics or passive, we use somewhere between 5 and 10% of the water that they do in California. Think about the water problems we have in California. We can grow food locally without the need for massive, we're not as water deprived here as they are in California, but the truth is, water is going to be a problem everywhere in the world. And parts of the world, that you probably are familiar with, water is a big, big problem. Well, if you could grow food with a fraction of the water, nutrients that you can bring in a bag, and LED lights that will last forever. And this LED light, by the way, I can take a solar panel that runs on 24 volts, plug it in here. This is 24 volts coming out of here. And this was running on 24 volts. suddenly you can have solar panels charging up during the day with batteries, and at night you turn them on and you power your good seed starting. And one of the things that I'm doing now and shooting the little YouTube videos that we just started is I'm using one of these and I'm starting 3 seed trays that are side by side by having it up high versus a T5 fluorescent that uses about the same amount of energy. So I could start 3 times as much area with an LED light source. So the LED light source is really what enables people to grow food at home, indoors, year-round. And some people say, well, I'm only going to want it for seed starting. But what happens, and this is, my father-in-law said it best. He's 78 years old and he didn't start growing until and he's 81 now, but when he started growing indoors, he was 78. And he says, Vic, the problem with this is it's addictive. You're going to want more of them. So he keeps calling me up and said, send me another one. I've got this I want to grow. I want to grow this. So it's just a lot of fun. It's a great winter hobby. And you can walk downstairs and get your own, this is my father-in-law's little vertical garden in his apartment. And the first time I saw what he did in the canning jar, he's the one that came up with it. He handed me that and then we took a picture. And his basil leaves are as big as my hand. I mean, they're really pretty incredible. So the things like herbs and lettuces are really, really easy. And really, the truth is, you can pretty much grow anything if you just play with it and experiment with it. And I can always help you with that as well. So these are the basic steps for setting up your system. If you take a look, what I did is I actually brought a jar that I put the fertilizer in. You can see it's got a little bit of a yellowish tint to it. You've got, in this case, the 3-inch net pot. I showed you that earlier, just drops right in. And then what I typically do is I leave like 1 layer of pellets low. You want to have the water so that it's maybe about 3/4 of an inch below. You don't want the seed to be in water, but you want it to stay moist because the clay pellets absorb the moisture. And then, I've got arugula here, I've got lettuce, I've got cilantro, all these different basils, all these different types of herbs, and everything pretty much works. So anything you want to grow, you can set up, and literally in 3 to 4 weeks, herbs take a little bit longer. I'd say herbs are more like 4 to 5 weeks before you can start snipping them. But you don't want to cut them all the way back. You just start cutting what you want. Have a salad. I usually get about 3 cuttings before they start becoming a little, they may not taste quite as good eventually, and then you just replace it. That's what's so nice about the individual canning jars, is because you can harvest them as you want them, restart them as you want them. If you're doing a large container, if you're growing exactly the same thing, it works great. But if you're growing different things, all of them germinate and grow at different rates. So what happens, or what I've learned happens, is some of them that grow fast, they drop their roots, they start sucking the water up, and then the ones that didn't germinate yet aren't in the water anymore, and they don't grow. So if you're growing things that grow at roughly the same rate, then get the bigger container. And what's neat about it is you can plant it, go to Florida on a vacation for a month, and come back and the plants are still good. There's a guy by the name of Dave Brearley who used to work at Molex who set up, I think, 3 or 4 of these in an old bathroom that he didn't use. And he said they went away to visit their kids in Virginia. 3 weeks, 4 weeks later, they came back and everything was nice and ready to go. So it's really a pretty cool way to do it. And it's the simplest way I've ever seen, because you don't have to water it regularly. The nutrients are already in there. The light turns on and off by itself, just due to a timer. And it's fun. I enjoy teaching people and showing people. And I don't know what else is in here. So, where you get these various pots and things, these are where I got some of the cocos and cannas and the fertilizers. This is actually where I got the the master blend, although I don't know if this company in Morris actually will sell it directly, because they, to us. They may want to sell it to a distributor. So those are basically the steps and where I got them and how to do it. It's really very, very easy. And like I said, if you take a look at the website on that page that I sent you, that has a lot of descriptions of how to do it.